start, and we are going to continue these things we have been discussing in the previous one. It's exactly a week, because I was absent. But anyway, I think that the topic is pretty important to finish the things right now on this. And the first question is is it true that it was the last slide you saw during the presentation? Yes. Okay. Some of you have this situation. Some of you for some reason don't. Okay, so let's see how we can describe the dynamics in a simplified case where we have only a quadratic problem, and let's discuss how things work out with and without momentum. So it's a good idea, this theoretical deployment, this theoretical machine learning, to simplify a problem a lot and see what's going on with it. What kind of analytical results we can describe in this way. And so let's do this. Okay, I hope yes. And let's see what's going on. So, again, can you see it? Right. So we have a quadratic problem, a quadratic optimization problem that consists of two terms. To minimize this thing. And the first term is a quadratic function of our number. And this quadratic relation is defined by the methods of pairwise interactions. Also we have linear term, and actually we don't care a lot about this term because it really affects little the probability solutions. And also we would assume that A has positive eigenvalues. And why do you think we need this assumption? Any ideas? Okay, let's put simple. Let's consider a quadratic optimization problem like this. Let's want to minimize with respect to W, and we have some negative eigenvalue. What would be a solution to this problem? And what would be the function, the value of this function for specific W star?
This will be the solution of minimization will be eigenvector corresponding to that minimal eigenvalue, and the function will be norm of that eigenvector by that eigenvector.
Yes, okay. Almost you are very precise about the idea, but let me write it down. So suppose we have some negative eigenvalue, and so in this case, if you have this eigenvalue that corresponds to negative, or eigenvector that corresponds to this negative eigenvalue, that would be the vector E, and we can say that it has the following form. Yes, we have minus lambda E transpose E. Yes? This guy is some positive constant, and so it's negative. But what happens when we multiply this E by some constant? Let A prime be A times E. We have A squared times this thing because we can move away this linear term and all operations are linear. And so now our function is like this, and we have the following value of the current function. And so if we have, okay, for example, we selected this thing for a scalar problem between these two guys being 1. In this case, our result is minus lambda a squared, where lambda is the minus negative eigenvalue, and it means that increasing a, we decrease the function value, and we actually can reach any negative value. If we increase a large enough, this thing would be smaller than any predefined constant. It means that, okay, makes it will simple sense to consider these problems, because the solution allows us to go to the minus infinity. And typically when we are talking about quadratic problems, we are interested in problems like this, where we have a specific minimum value, and this minimum value can belong to some specific number.
We don't see your plots. We don't see your plots because of
let's fix this. Okay. And also we can do this thing. I hope it will be there. Yeah, so you have a common parabola, like, okay, let it be the w squared plus b, and you can see the minimum value is b. Is it okay for you?
yes.
Okay. And okay, the exact value w star is 0. So in this case it's okay. And we can see that we have only positive eigenvalues in this matrix actually. We have a single eigenvalue that equals to 1. Because it's a matrix that consists of a single number. Okay, so we now have a problem with positive matrix. Eigenvalues are from lambda 1 to lambda d, and we can say, actually, it will be an exercise for you. What is the difference between the function value at wk, a specific iteration of gradient descent? Yes, we run a gradient descent for this quadratic problem and obtain wk at case iteration. Then we have w star. It is the value of this input vector that corresponds to the minimum value of this function e of w. And so we are interested in how fast we converge to the true value. So that's it. And actually, in this case, we can describe the state of convergence in an analytical way. So suppose we have some wi0, it means i's component, and w0 is the value of this vector at the zeroth iteration. And actually, this is not a problem. No, some positive number that's here. Then we have this part that corresponds to the eigenvalue, and it doesn't depend on the iteration. But then on the left, we have a term that depends on the number of iterations. Alpha here, you can guess what it is.
It is learning rate.
Yes, it's learning rate. And we see that this dynamics is a power dynamic, so if this guy is closer than 1, is smaller than 1 by absolute value, it decreases to 0 eventually, yes? So suppose if this guy kind of has absolute value smaller than 1, then this following term has this quadratic ratio of convergence. If this guy is bigger than 1, okay, it quadratically increases. So we don't observe the convergence if the absolute value of this guy is bigger than 1. Yes, so okay, we need to select alpha such that we have depth of the convergence. Also, you can see that for any finite lambda, we can do this. Yes, we just need to select alpha to be small enough. If alpha is small enough, all these lambdas are kind of some positive numbers, and multiplication by small number, we have something that is smaller than 1, but actually very small alphas are not very good option as well, yes? Because in this case, this difference would be close to 1, and our conversions would be very slow. Actually, we would be multiplying sync, that is kind of something like, let it be, lambda be ai, and we multiply a for 2k times. And in this case, if ai is close to 1, then this sync would be very very small. Yes,
I'm extremely sorry for this simple question, but can you explain where is the x in our error? Where is the input? Like we have a function of loss dependent on the weights, but I can see the input.
Okay, we don't care about input in this case. For example, you can consider a linear regression problem, yes? For linear regression problem, we have something actually, if you look at the quadratic term, the quadratic term would be, what is the matrix between these two guys for linear regression? Any guesses?
X squared, like xt by x?
Yes. This guy. And it means that really, for example, linear regression problem is a quadratic optimization problem with the following.
So right now we only care that we are optimizing W and everything else.
Yes, we don't care.
Okay, thank you.
Because we suppose also we can see that for narrow networks, it would be much harder to guess what's inside this. Actually, we can say that we can assume that this problem is close to a quadratic problem, and in this case, this matrix A would be the matrix of the partial derivatives of the loss function. The second partial derivatives, dl, w, I, w, j. Yes, it's when we are doing a Taylor type decomposition of our loss function, we would obtain a quadratic term that would be like this here. Also, one comment on relation between this optimization problem and, for example, linear regression. If you look at this matrix is a non-negative definite, as we discussed closer to the beginning of the course. Because it's a product of two matrices, a matrix and the transpose of this matrix. So, let's go back to this formula below. So we have a sum a from 1 to t, and we want all these guys to be as close to 0 as possible. Because if they're close to 0, then we have the maximum speed of the convergence, yes? Because it leads to the fastest possible decrease of this circle. And in this way, we have only one parameter now to affect this speed of convergence. We can vary only the learning rate alpha here. And so we want to select alpha to minimize the maximum absolute value of this guy. So we want to this alpha lambda I absolute value maximum with respect to I to be as close to 0 as possible. Yes, so we want to minimize with respect to alpha this function. And actually it means that we want it for one side to be as close to 0 with the maximum eigenvalue, and for other part it would also be as close to 0 as possible, but from the other side. So let's suppose that alpha 1 is the minimum eigenvalue, so we have sorted eigenvalues, and our lambda d is the maximum eigenvalue, and by selecting alpha, we actually see what's going on. And actually this guy is equal to 1 minus alpha lambda 1 and 1 minus alpha lambda d. Yes? Because everything else goes in between these two numbers. Agree?
They are sorted by absolute values, yeah? Lambdas are sorted by absolute values.
Yes. We are interested in absolute minimize also absolute value to this guy because we take a square here. Yes, we take it, it's a power of 2.
Absolutely. All lambdas are
Do you understand? No, not you. I listen to understand and for you. What is the answer to this question?
So, but if all. Okay.
Okay. So basically, yes, this maximum is equivalent to this maximum, only often now it corresponds to the minimum as the maximum eigenvalues of this matrix. And so we want to find the guy alpha that corresponds to minimizing this functional. And actually, it happens to be this thing. Because in this way, you can multiply, for example, the first part. Wait, we obtain 1 minus 2 lambda 1 divided by lambda 1 plus lambda n, lambda g, lambda g. And okay, let it be an exercise for you. But we have this rate of convergence and the I'm sorry, I lied to you. Actually, alpha star that minimizes this number is like this. And when we are doing an exercise on finding specific ratio of convergence, we would obtain, okay, let me do this. Okay, I think I need some place to write more formulas. Okay, let it be like this. So basically, we select alpha such that it equals lambda g divided by lambda 1 minus 1 divided by lambda g divided by lambda 1 plus 1. And let's see what would be the range of convergence for the specific alpha star. 1 minus alpha lambda 1 equals to 1 minus lambda g divided by lambda 1 minus 1 divided by lambda g plus 1 times lambda 1, and it is 1 minus lambda d minus lambda 1. We multiply the denominator by lambda 1, and in the bottom this is right here, and we can actually see what is going on and how we can describe the convergence ratio, and you can see that it would be the same if we would subtract from 1 alpha times lambda d, but with the opposite side. With the opposite side, yes. And that we can, if you want to continue this derivation, you obtain exactly what's written in this slide here. And we see that the ratio will be like this. Okay. So we can do this. And we also see that selection of candidate is a pretty important thing. Basically, we can say that it affects convergence to divergence of the problem. Selection of too big alpha leads that we would have this guy to be smaller than minus 1, and it means that we have a divergence of our condition. If you select alpha to be too small, we obtain the convergence, but it is very slow, because this guy would be very close to 1. It's not a good thing. So there is some optimum in between these two things, and we can calculate this if we know exactly the problem is solved. And actually we can do something similar for our method with momentum. If we add momentum to our thing, we obtain the similar picture, but a bit more complex. So basically, before we were interested in actually alpha lambda I between this guy and this guy. So in this case, the absolute difference between 1 and this number is something between 1 and 0. But if we add momentum, the picture is a bit different. We say that we have more freedom for our alpha and for our lambda. Basically, we increase the right side by 2 beta. The beta is the coefficient for our momentum. And it means that our conversion conditions a bit nicer. And also, what is even more important, we can increase the conversion speed selectively. We can find alpha and beta such that in the end the convergence is possible. And actually we can draw a picture like this. We have momentum here on one axis between 1 and 0. We have also we have alpha here between 0 and 4, and we see the convergence ratio for typical optimization problem, depending on the values of beta and alpha. And as I told to you, for a simple problem with eigenvalues, we have 0 beta, and we have a bound between the case when everything converges and the case when everything diverges, this black area. As we increase the momentum, the area where we observe the convergence increases. And so we are in a better situation. Moreover, by selecting appropriate beta and alpha, we can increase the convergence speed in our problem. And that is what we are actually doing in momentum. It is beneficial and so on. Also, you can find and draw some pictures on how everything looks like for different pairs of alpha and beta. And for example, here, the C here, if we select alpha to be 1 minus r lambda, we have very fast convergence when we start from special range. Typically, we don't know lambda, so this would be lambda. So yes. What is R matrix? R matrix is something that we have as this. Think actually, instead of considering a big matrix, we say that we have a matrix R that has 4 elements. It's beta, lambda I, then we have minus alpha beta, and 1 minus alpha lambda.
Just 2 by 2 matrix.
It is a 2 by 2 matrix, so it has 2 eigenvalues, and we can find out what's the value.
And what is lambda I here?
Lambda I, as far as I remember, it is, okay, I can't remember exactly, it should be something like, I suppose we consider all possible indexes I from 1 to d and define a matrix Ri for specific eigenvalue and observe the convergence ratio for specific eigenvalue for specific term in this convergence rate here. So it would depend here, but maybe it's an error, that's what I'm saying. You can check it on your own if you want. It's not that hard to do so, actually. One more time, this matrix, eigenvalues are easy to find. Okay, for they have a form a matrix 2 by 2, And given that we obtain the convergence speed, that depends on maximum of these two guys. And given that we can optimize the convergence ratio by optimizing alpha and beta. And actually, we can say that it's a bit different than what we have seen before. When we optimize alpha and beta with respect to the convergence speed, we would obtain alpha star that corresponds to fastest convergence in this form, and beta is a following basis. And also we have an update of the convergence speed. It was like this before, where k kappa is a conditional number, and now we take the square root of the conditional number, and conditional number, not the ratio of lambda n divided by lambda 1 plus 1. And so we say that this guy is bigger than 1 because lambda n is a bigger eigenvalue than lambda 1. And by taking the square root, we increase the convergence speed here. Proves that we will obtain faster convergence rate in the end. And this means that by introducing momentum, we can do better than what was before. Also, you can look at these formulas and try to find out what are the optimum rate of convergence and optimum momentum. We suppose that these two guys should be pretty big, and so alpha should not be too big because we divide 2 by this simply and take square or take square. So we prefer, pretty small learning rates. Here we also have some intuition on how to select beta. Basically, we can say that this lambda n is typically much bigger than lambda 1 in most problems. It means that this thing is approximately lambda n minus epsilon divided by the square root of lambda n plus epsilon squared. And it means that this guy is something slightly smaller than 1. And this is actually the momentum coefficient that usually used in applications, something like 0.99 to 0.999. So in this case, here I bring us the results that we can use in applications. So now we have recomposed our problem to the case of, for simplified case of square root problem, where we have a square root dependence of the output function and the input, and we can see what is going on. Okay. And that's actually what I have said before, but let me introduce it one more time to you on how to select momentum and how to select the rate. So basically, we set the momentum high, pretty close to 1, and then we can choose rate to obtain the goods. Also, in real life, when we are talking about the real optimization of neural networks, we have what? We have little knowledge about lambda 1 and lambda 2. So basically, we should do it experimentally for alpha and hope for the best. Okay. Any questions regarding this one? Yes?
You say that we should choose momentum close to 1, but on your graph, the minimum was for rather low momentum.
I suppose in this case we consider it a specific eigenvalue here, but actually we are taking kind of multiple curves that correspond to different eigenvalues and part. So I suppose the maximum will be pretty close to 1, but maybe a better answer to this question exists.
Okay.
Any other questions? Okay. So what else we can do? Again, let us recall the formula of what is going on actually in models. We update the vector parameters in the following way. We have vector parameters, the previous iteration, and we add some coefficient here. And this thing consists of two terms. We take a new gradients as the point wt, multiplied by learning rate that can depend on the iteration number t, and also we add some part from the previous iteration, what is called the momentum. And this is the basic formula for the gradient descent with momentum, and one idea on how to make it better, maybe a bit off-road if you're talking about the modern application practice, is to say, let's calculate the gradient with slight change in the point where we calculate it. Basically, we can assume what would be the next direction, what would be the next step, at least approximately. We take the previous W and we add mu times Vg minus 1, and this is exactly this thing, yes? So we expect that this Wg plus 1 will be close to this guy, and in this way we will be calculating the gradient in a better point. So we can use this empirical procedure to somehow accelerate gradient descent. It is named after the person who invented this, Nesterov, a very famous optimization guy who did a lot in this area before it became very popular for mathematics. Okay, the next natural idea on how we can do this, how we can improve the convergence rate of optimization, is to use the second order methods. Please raise your hand if you know what is a Newton approach to the second order optimization. Okay, you can do it higher. Okay. So basically, what is the idea? Before gradient descent, basically what is doing the gradient descent? We say our function is close to some linear function.